Hello and welcome back to another video, guys. Meta has done it again and released the Llama 3 model, which comes in an 8 billion and 70 billion variant. And from the first feedback that I've heard, those models perform really well. And in this video, I will show you how you can run both models on your local computer. And yeah, I would say let's just jump right into it. And accompanying to this video, I also wrote a Medium article, which I already published 2 days ago. And here in the start, I showed the key changes of the Llama 3 model. So before we actually start running the Llama 3 model on our local computer, I quickly want to show you the key changes and explain how the improvements from the Llama 2 models to the Llama 3 model were possible and what the Meta team has done to accomplish such improvements. And yeah, the first thing is that the Llama 3 model achieves a 10% relative improvement compared to the Llama 2 model on the same parameter scales. And the new Llama 3 8 billion model sometimes even outperforms the Llama 2 70 billion model, which is kind of crazy thinking how much less parameters this model has. And as we will see later, most of the improvement just comes from training the model for longer on more tokens. But more on that in a second. Then maybe that's something you already assume. Both models are state-of-the-art in their respective parameter scales, so achieving the highest scores on various benchmarks in their respective parameter scale. And then the context size increased from 4,000 tokens to 8,000 tokens, which technically can be increased even further. And then finally, both models, the 8 billion and the 70 billion parameter models, were trained on 15 trillion tokens, which is 7 times more compared to what was used for training Llama 2. And this also includes 4 times as much code tokens or code data, which is compared to Llama 1, which, if I remember correctly, was trained on 1 trillion tokens, and then Llama 2, huge step to 15 trillion tokens for pre-training both models. And as Meta states in their official blog post introducing the Meta Llama 3 model, in the coming month, we expect to introduce new capabilities, longer context windows, additional model sizes, and enhanced performance. And something that I'm very curious about, we will share the Llama 3 research paper, which I think will give us even more detail on how they built the Llama 3 8 billion and 70 billion and all the other coming models. As they state here, they release a pre-trained and an instruction fine-tuned language models with 8 billion and 70 billion parameters. I think by now I mentioned that often enough. Then one of the capabilities that they achieve with those models is especially an improved reasoning. We believe these are the best open source models of their class, period. And I think, while this is a bold statement, later they get even more direct and say, not just they believe it, but they actually know it, kind of taking into consideration evaluation benchmarks and their goals for Llama 3, the near future, to also make it multilingual and multimodal, to have a longer context, and continue to improve overall performance across core LLM capabilities such as reasoning and coding. So I think all of us are definitely also looking forward to such improvements. And then, as I mentioned, they get a little bit more direct about what they believe about how good Llama 3 is. And they say, thanks to improvements in pre-training and post-training, our pre-trained and instruction fine-tuned models are the best models existing today at the 8 billion and 70 billion parameter scale. And yeah, there's your bold statement. And from what I've heard so far, this is a legit statement from Meta. Also considering the 15 trillion tokens they trained both models on, I think there's no model in the respective parameter scales that was trained on more tokens. So it doesn't make very much sense that those models are the best performing. Yeah, and as I mentioned also here, they greatly improved capabilities like reasoning, code generation, and instruction following, making Llama 3 more steerable, which is awesome. And then they dive into how they made the model better and what they believe are the pillars on how they improved Llama 2 to obtain Llama 3. Here they say there are 4 key ingredients: the model architecture, the pre-training data, scaling up pre-training, and instruction fine-tuning. And with the model architecture, they didn't do any, let's say, major changes, which also make the 10% relative improvement from Llama 2 to Llama 3 more mentionable or more impressive. One thing they did is they used a new tokenizer, which a vocabulary of 128,000 tokens. The one before had 32,000 tokens, so that's a 4 times increase of vocabulary size compared to the Llama 2 model. And they state here that this leads to substantially improved model performance, something I find very interesting, or a cool insight, because I feel like I haven't seen much more models doing that before, looking into like the impact of the tokenizer. So that's definitely a very valuable insight from the Meta team. And another thing they added is the group query attention, which they already used in the Llama 2 70 billion parameter, but now also added to the 8 billion variant of the Llama 3 model. And those are actually all the architectural changes they've made. And when I earlier said there are no major changes to the model architecture, I was referring to the fact that they stayed here. They used a relatively standard decoder-only transformer architecture, which they also used in the Llama 2 model. Just from an architectural point, we have seen with Mixtral, a mixture of experts architecture, but they haven't used anything like that for the Llama 3 model. And therefore we can also kind of assume that most of the improvements actually just come from training the Llama 3 model for longer on more tokens. And yeah, I just wanted to clarify when I earlier said there are no major changes to the architecture, what I actually meant by that. Later in the article, the Meta team then also mentioned that the new tokenizer offers improved token efficiency, yielding up to 15% fewer tokens compared to the Llama 2 tokenizer. So imagine both the Llama 2 and the Llama 3 model generate the same amount of tokens per second. This would mean that you still get more actual text because you need less tokens to represent the same string. And with additionally adding the group query attention to the 7 billion or 8 billion parameter Llama 3 model, they observed that despite the model having 1 billion more parameters compared to the Llama 2 7 billion parameter model, the improved tokenizer efficiency and the group query attention contribute to maintaining the inference efficiency on par with Llama 2 7 billion. So while having the same inference speed, we just get additional 1 billion parameters to, for example, improve capabilities like reasoning. Then we can jump to the next key ingredient, which is the training data. Unfortunately, it seems like the used training data will remain closed source, which was also the case for the previous Llama models. And as I already said, they used over 15 trillion tokens collected from publicly available sources, whatever that particularly means. And as I already mentioned earlier as well, the dataset used is 7 times larger than the one used for Llama 2 and includes 4 times more code. I know a lot of people in my audience are also interested in large language models for other languages than English, and that's good news. They also prepared for upcoming multilingual use cases. Over 5% of the Llama 3 pre-training dataset consists of high-quality non-English data that covers over 30 languages. While 5% doesn't sound that much, I think in practice it always turned out to be pretty good when being fine-tuned for other languages. So let's see how future versions will perform and how the multilinguality will be for the Llama 3 model. And here they make a little bit more statements about how they collected the data set and how they kind of filtered and cleaned their data set. But this is like very vague, and I hope in the research paper they will elaborate in a little bit more detail how they pre-processed the training data. And then the third key ingredient is scaling up the pre-training. And again, I'm looking forward for the research paper, because also here they're talking about that they have developed a series of detailed scaling laws for downstream benchmark evaluation. These scaling laws enable us to select an optimal data mix and to make informed decisions on how to best use our training compute. Importantly, scaling laws allow us to predict the performance of our largest models on key tasks. So I'm not sure if they have certain metrics or laws which data mix to use to achieve a certain capability. For example, specific data for reasoning, or you want to obtain at least 20% for a medical benchmark and therefore train the model for a certain amount on medical pre-training data. So also here, I think it's a little bit vague, and I'm not 100% sure how those scaling laws will look like, but I just hope for the research paper to get more clarity on these. And then there's another very interesting statement, which I definitely want to highlight, is that while the chinchilla optimal amount of training compute for an 8 billion parameter model corresponds to roughly 200 billion tokens, we found that model performance continues to improve even after the model is trained on 2 orders of magnitude more data. Both our 8 billion and 70 billion parameter models continued to improve a lot linearly after we trained them on up to 15 trillion tokens. And here's a very important statement. Larger models can match the performance of these smaller models with less training compute, So technically it would be wiser to initialize or use models with more parameters, because you would get better scoring models or more capable models with less compute spend. But smaller models are generally preferred because they're much more efficient during inference. It's kind of like the trade-off during training. You have to spend more compute to get a more capable smaller model, or you have a bigger model and need to spend less compute during training to get kind of a similarly performing model. But then during inference, you always have to spend more compute. So I guess in the long run, the calculation will work out, but a very valuable and interesting insight. And then for the last key ingredient, the instruction fine-tuning, they state that their approach to post-training is a combination of supervised fine-tuning, which they also used for Llama 2, but then also used rejection sampling, proximal policy optimization, and direct policy optimization, which were not used for instruction tuning Llama 2. And then something they already highlighted in the Llama 2 paper is that the quality of the prompts that are used for supervised fine-tuning has an outsized influence on the performance of aligned models. And here they also say that it's not just for the supervised fine-tuning, but also for the preference rankings that are used in PPO and DPO. So one more time, it looks like for aligning and instruction fine-tuning, having high quality examples is very important. And yeah, here they say some of our biggest improvements in model quality came from carefully curating this data and performing multiple rounds of quality assurance on annotations provided by human annotators. So yeah, they really make a point here. Make sure that the data you're using for instruction tuning and fine-tuning the large language model is of high quality. And then one more thing that I would like to highlight here is that they found that if you ask a model a reasoning question that it struggles to answer, the model will sometimes produce the right reasoning trace. The model knows how to produce the right answer, but it does not know how to select it. And training on preference rankings enables the model to learn how to select it, which is also a very cool insight. So definitely proving that the use of proximal policy optimization and direct policy optimization helps a large language model not just only to kind of like generate the right reasoning trace, but also being able to select the one that is actually correct. And I think especially if you perform something like chain of thought, that is very valuable. All right, and I know this has been now a full deep dive into the Llama 3 model, explaining all the details and backgrounds behind it and what major changes have been made to train such a powerful model. And there's one more thing before I now will show you how to run it on your local computer, which is the section What's Next for Llama 3. And the Meta team here has published some benchmarks or scores on various benchmarks for a new model that is not published yet, but apparently it has 400 billion plus parameters. So probably also not a model for the scope of this video, because running such a model on your local computer will be very, very challenging. I mean, like even with 4-bit quantization, we would need 200 gigabytes of VRAM. So I think you only can run such a model on multiple GPUs, and therefore it's not really relevant for this video anyway, but I think it's very cool to see that Meta plans to release also such a powerful and huge model. So seeing those scores, they are definitely similar to GPT-4, potentially performing a little bit worse right now, but as you can see, it's also a checkpoint and it's still training. So as we saw from Llama 2 to Llama 3, the longer the model is trained on more tokens on, the better the model will get, and potentially we will see that this 400 billion model can even surpass GPT-4, which then would actually be pretty crazy. But I think soon enough we will find that out. In case some of you are interested in how I actually highlighted this blog post with those text marker style highlights, for this I used a Chrome extension which is called Web Highlights, which was actually built by a really good friend of mine. So in case you're interested and want to highlight some documents like this, you can also highlight PDF documents. Make sure to also get this Chrome extension, which I really like, and I will also link it in the description box for you guys in case you're interested. All right, and now let's finally run the Llama 3 model on our local computer. All right, and for this I wrote a quick and lightweight file which is called Llama 3 local, and I created a Github repository which you guys feel free to check out and to run the Llama model on your own computer. So the steps that are needed if you want to use this repository is to clone the repository by running these two commands, then install required dependencies, And finally, we can use or run the UI and interact with the Llama 3 model by running this statement. And let's have quickly a look into the Python file. We are using the vLLM library. In case you haven't heard about it, I know that the Transformers library from Hugging Face is the most popular, and I also really like to use the library. The only thing is, using the vLLM library, we can speed up the inference of large language models by 2, 3, 4 times depending on the GPU that you're using, because that's kind of the specific purpose of the library, to allow super fast and high speed inference. And the library only had one LLM class which didn't allow to stream tokens, kind of like iteratively streaming them instead of basically waiting for the whole text to be generated. And for this I had to adjust the LLM class a little bit and write my own class, which you can see here. As you can see, it's super lightweight, not much code. So what I'm basically doing is I initialize an engine, which is more or less our LLM. So we can generate text with this one. And then we have a generate function that iteratively yields the generated tokens. Super briefly explained the streaming LLM class. And then we have also an UI, which I will use Gradio as a supporting library that does all the heavy lifting for me, more or less. And here we will pass the LLM, the tokenizer, and the sampling parameters. This is our generate function that is necessary for the Gradio chat interface. The chat interface will invoke this function and will pass a message, which is our current user prompt and the history of user and assistant chats. So kind of have this history chat format where you first append the user instruction, then the assistant response, and then we append our most recent user prompt, which is the message here. And then using our tokenizer, we apply a chat template, and we can see an example of the chat template here, which is defined in the tokenizer config of the Meta Llama 3 8 billion instruct model. And here the chat template, we can see it loops through the messages, and for each message in the loop, we'll then start with the string with the start header ID, indicating that now we will pass the specific role. So it could be system, user, or assistant, and then the end of the header ID, so another specific token. And then we have 2 new line breaks, and we'll then pass the actual message. So that could be an instruction by the user or the assistant's response. Trim this string, and then we have our end of text ID, so kind of our end of instruction or end of text ID to indicate later in practice that the model is done generating. And then at the end, we will add a start header ID assistant, an end header token, kind of indicating, okay, this is our history. And then we have our start header assistant and end header tokens indicating, okay, and from now onwards, we would like to have the response by the assistant to the history. And then, as I said, we will pass the prompt and then generate iteratively tokens and yield them. And that's more or less all. Then there's one launch function which starts our UI. And as you can see here, so first we load the streaming LLM. This is a Hugging Face ID. So on Hugging Face, you can find the repository here, Casper Hansen, who already published a AVQ quantized version of the Llama 3 70 billion instruct model, which I will use. And then, since this is a quantized version, I also need to pass a quantization parameter here and the data type. In case you want to use a different version, either feel free to adjust this, for example, to the 8 billion here, or use the official Meta instruct model that's not quantized, but then you also need to remove this one and maybe adjust the data type to bfloat. Just keep that in mind. Yeah, then we just assign the tokenizer. Those are the default sampling parameters from the Llama 3 Github repository. So we have a temperature of 0.6 and a top p-value of 0.9. Max tokens is 4096, but feel free to adjust this value as well. And in the start, there was an issue with the stop token ID for the Llama tokenizer. It might have been already fixed, but here I needed to specifically add the termination token, EOT, or end of text token, so that the model knows it has to stop generating text when this token occurs. Yes, and then we can pass those to the UI and launch the UI. And once this is done, you can access the UI in your local browser. All right, and then we can first clone the repository by running the following cell. Once the repository is cloned, We can then install all required dependencies, and then finally we can run the UI and start interacting with the Llama 3 model. And for this we run the following statement, and here you can see that we're initializing the LLM engine. This can take a minute, especially if you're downloading like the 70 billion parameter model, depending on your bandwidth. This can take more or less downloading the model weights. All right, yes, and now you can see that the model was successfully loaded, and loading the model weights took 37 gigabytes of VRAM for loading the Llama 3 70 billion model, and it only took 37 gigabytes because I used the AWQ quantized version of it, which is 4-bit quantized, so each parameter just needs 4 bits, and therefore it's around 37 gigabytes in total. So what I would always recommend you is to see how much VRAM you have available. It is often better to use a model with more parameters with less precision, so for example a 4-bit quantized, than using a model with less parameters but in a higher precision. For example, I would recommend you to rather use a 13 billion parameter model, which hopefully also will come soon for Llama 3, with 8-bit precision or 4-bit precision, instead of using a 7 billion or 8 billion model with 16-bit of precision, depending on how much VRAM you have accessible. But usually you can generate text of higher quality if you use more model parameters with less precision in your compute budget. And then we can click on this link and access our UI, and here you can say, "Hi, how are you?" And then we can see here the model's response, and as you can see, the generation of text is also super fast using vLLM, and I'm personally also using an RTX 6080 GPU, which NVIDIA was kind enough to send me to support my YouTube and Medium channel, and the RTX 6080 GPU has 48 gigabytes of VRAM and 568 tensor cores, and therefore allows me to generate text using the Llama 3 70 billion parameter model very fast. And obviously, as we can see here, I'm just a language model. I don't have emotions or feelings like humans do, so I don't have good or bad days. I'm always on and ready to assist you with any questions or tasks you may have. How can I help you today? Obviously, the model is capable of way more than replying with this text, but that could be something for a future video. And yeah, now it's your turn to explore the capabilities of the Llama 3 model. Yes, and that's it for today's video. I hope it helped you understand what is new with the Llama 3 model and how it improved in regard to the Llama 2 model, and also how you can run it on your local computer using the vLLM library, allowing you to generate text in a very fast way, and using the Gradio library to have a beautiful user interface, and both being super lightweight and easy to use. And yeah, from here on, have fun interacting and using the Llama 3 model. I hope you have a great day, and I see you in the next video. Bye bye.